Welcome to this tutorial 2.2, which is about understanding more practical applications of the torsion theory that we looked at. We have already practiced set of 2-3 problems as we discussed these mathematical foundations and the physics framework of the problem, as we looked at stress functions, the Prandtl function. In this tutorial we are going to now summarize everything about the torsion, not of course the airy stress function tutorial that which we already have, but more about these warping functions, solving few sections, understanding this torsional rigidity J as more important point. Just to summarize one concept, we looked at this concept of torsional rigidity, right? Where we use this equation T is equal to G J theta dash, where this is constant, this is material property, and this is a loading condition. What we basically said is for this given twist, right, which is this war, J is of extremely important value because that dictates how much twist is going to happen. And this is extremely important in impedance in terms of aircraft structures, by the way. This is one of the first qualitative tutorial problems you could consider. This sheet, which is open and not resisted to do any functional change, which is unrestrained from any warping, right? See how easy it is to bend this sheet. These are open sections, right? Moment I glue them, it becomes more complicated. You see how it is easy, right? The J of these hollow structures are extremely small. You can easily do it. Look at this marker. Small cross-section area, solid, barring this. See, you cannot see any visible warping here, right? Cannot see. J is high. Right? So J plays an extremely important role because your wing structure, which is going to have this cross section and aerofoil structure like this, is completely governed and dictated by the choice of the material, which determines G, of course, and then the structural property itself determines J. So this would determine my J, and in turn then for a given torque I could see what is twist. Where does this come into picture? Elasticity, aero-elasticity problems. See, this is my one section of the wing, right? So I'm just going to explain this as tutorial problem 1. It is not a GATE problem, it is not competitive objective problem, it is a theoretical problem. What is the role of structural torsion in the aerodynamic analysis? And I could make it an objective question as saying that option A, it increases lift, B decreases lift to something. But let's understand this phenomena very, very clearly. Then in lifetime you will never forget this importance of all these 3 parameters and the theoretical framework that we looked. There is going to be torque as we discussed, right? These are the different wing sections. I am going to call them 1, 2, 3 just for convenience. Some next to middle, almost towards the end, right? Extreme edges we will ignore because, as we said by St. Venant's principle, some of these end effects of stress are local, so we will ignore. This is the root cord, which is attached to the fuselage. This is getting distributed with lifts, right, and its twisting moment, which means the torque which is generated by aerodynamics is going to twist this wing. So if this was my initial sectional view, the view from this side, if this is the aircraft which is parked, I am looking at it this way. This is the aircraft parked, you are looking at it this way, almost like a line, right? It is going to have this twist, and this twist is going to cause each of these 3 sections, section 1, section 2 and section 3, to actually increase in their angles. These are going to form different angle of attacks. My goodness, aerodynamists suddenly have a worry. So at section 1, angle of attack is alpha. Then here it is alpha plus theta 1. Here it is alpha plus theta 2. So as wing is getting twisted, it is actually seeing more angle of attack. That may be good or bad. If this increases, lift goes up. Right? Imagine these are small enough so that it is still not stalled. Then lift has gone up locally here, which means lift no longer is constant, but has suddenly gone up something like this. Added lift is going to create further movement, which may further twist it. So there is a coupling involved. This is called aeroelasticity, and that's the role of structures. So with this torsional theta dash, the twist that wing brings in, the lift distribution becomes non-linear. It increases towards the edges slightly, further enhancing this tendency to twist further, and at some point when theta becomes large, lift drops drastically over those sections because of stall, local stall, and then these vortices, eddies, get formed. If sufficient energy is built, this may call resonance, increased tension here, and this energy dissipation is going to cause wing to get fractured. That's the outcome of aeroelasticity. See how important is this foundation for aircrafts, right? So this was our problem 1. Now let us look at some other practical problems. The second practical problem which we will look at is, we have already seen this, but we have to find out now. For a circular cross section, K r square minus a square is a valid Prandtl's function. This stress function can be applied to solid cross section which is circular in nature of radius a. We are asked to find out d theta by dz, warping function w or psi, which is our Saint-Venant's warping function, of course the rate of twist, and inertia of course we know, so we will not do it again, and tau zy and tau zx. Okay, so this is our problem number 2. Now implicitly, by knowing, I know the second order magnitude is going to be constant, 2k, right? So del square phi is going to be 2k. Not a big deal, right? And there is anyway not a big deal in this. I already know it. Now moment I know this, what further thing I know is about the point that I have to look at this in a way such that I can find gj theta dash, right? So if k is required to be found out, so 2k is this constant, right? Del square phi. Correct? Now if del square phi is 2k, what I can simply do is t, right? Now g into d theta, g d theta by dz, right, is equal to del square phi. So which means that there is nothing but one important relationship which gives me, I'm just looking at the theoretical term which is called to this, which is used, not the rigidity, but the theoretical term which solves these equations, right? And I'm just trying to look at these to get better understanding. So the theoretical term for now we can park if that is a problem, but the whole aspect we are looking at therefore from this theory is the following, right? So the constant of integration is known, right? We also know that if this is the case, g d theta by dz is k, I can substitute this here. So my phi becomes g d theta by dz a square minus r square, because see the negative sign, right? It was minus of this. And then phi dx dy, the second moment of it is going to give me the torque, right? So the second moment of inertia which is going to give me the torque will also help me understand that what is the rotational inertia. So if I integrate this phi dx dy, what I am going to be seeing is gj theta dash. So this is torque, right, which is g j d theta by dz. So this is going to cancel from both the sides, and all I am going to left with is that I, or the rotational inertia, is pi a raised to 4 upon 2. This equation also we looked at, right? If this is the case, my d theta by dz, which is the first quantity which is asked, is t upon g into j. So d theta by dz is found out, right? So my first question is known. Now warping function, right? In warping function, we looked at that there are the two governing equations that are important, right? First of all, most important thing is you have to have a function which satisfies and solves the conditions which are del square psi is equal to 0. Psi on the boundary is going to be 0. Circle is a symmetric problem. Imagine now psi was a function of xy. That would mean this warp is more than the other warp. But then just by reversing the frame of reference, I would say different torque. Right? See this induction argument which I am doing. For a solid cross section, when this disk is going to move, if I just shift my coordinate frame, W would change. But circle is doubly symmetric, so this just by changing frame should not change, which means psi has to be 0 everywhere. Circular cross sections of solid nature have no warping, they have pure twist. The rods have no warping but pure twist, and that is extremely important answer. Once these are known, d theta by dz is known, right? It is easy to find tau zx, which is del phi by del y, right? What will this be? Since my phi is known, so I can substitute this as y, and I can get this as, since r is equal to a cos theta x square plus y square, right? So we can differentiate this. So the answer that I will get is tau zx. So we have to look at tau zs and zr. What is this stress in these directions and stress along the surface, right? I can work in polar coordinates here. So then tau zs is going to be del phi by del s, right? Just the mathematical framework here, which is Tr by J, right? Because that's how it has to be. The theta dash is going to come. Tau zx is minus Ty by J. Tau zy is Tx upon J. This is also clear, because the factor of 2 will cancel. This is going to be substituted as x square plus y square, right? So we have solved this problem. But the important outcome of this is that it is a symmetric function. Circular sections have 0 warping, which is some very beautiful outcome. Right? Now let us look at a bar which has a elliptical cross section. So this is problem 3. X square upon a square plus y square upon b square is equal to 1. In this cross section, we have to choose a function. We will choose it again, a symmetric function like this. Because we have to make phi equal to 0 along the outer surface, right? So for this elliptical cross section on this outer surface, this identity will always be true. So I have smartly chosen this function. If this is the case, then what I will get is by double differentiating this, 2c 1 upon a square plus 1 upon b square, right? Del square phi by del x square, which is going to be 2x and then 2. So 2 is going to come out from both the sides. Y square is here, is going to be minus of 2g d theta by dz. This analogy, del square phi is equal to constant, and this constant f is minus 2g theta dash. See our theoretical framework, which means c is nothing but g theta dash. We will start calling this as theta dash. 1 upon a square plus 1 upon b square. This is the constant that is known. Now, once I know this constant, I have to integrate these two. So integral of phi dx dy would simply be this g theta dash upon this entire thing is going to come out, right? So I am still calling it c because we have already found out c, into double integral of 1 upon a square is going to come out. So x square dx dy plus 1 upon b square y square dx dy, right? This is the term, and this is nothing but 2 into the torque. So torque is nothing but this. So 2 is going to be here, right? Because 2 into this integral is torque. We have seen this equation. This is slightly complicated in ellipse to find out. what we have to do is to integrate this dx dy from x varying from 0 to a and y varying from 0 to b. We are very clear, right? X square dx is what we have to look. So x cube upon 3 into b, right? And a cube upon 3 is what going to come out. So b into a cube upon 3, and since it is a by 2 minus a by 2 to plus a by 2, because the coordinate frame is such that you have to integrate from minus a by 2 to a by 2, a cube upon 8, so a cube upon 4 will prevail here, a cube upon 8 minus minus plus, so a cube upon 4 into b, correct? And pi is going to be because of the theta, so pi, this is the second moment, so pi a cube b upon 4 and pi a b cube upon 4, these will be these two integrals, right? When I differentiate, then this will become pi ab, this will be also pi ab, so pi ab upon 2 into 2c, so pi ab, the area of the ellipse, is what I am left with. See how beautiful analogy is. Minus dx dy, never forget. This we only got for this outcome. What about this, right? This is also pi ab, right? So the extremely important analogy is to look at this and say, what are the governing points? Is this 0? No, because you have this half, right? So this is 2 pi ab, because we have looked at this, pi ab upon 4, so pi ab upon 2 minus pi ab, which means the remaining residual is minus pi ab upon 2. So the net integral here is going to be g theta dash a square plus b square, a square b square is going to be here, right? That is going to come out 2, and then this is pi ab upon 2, minus minus will go, so pi theta dash a cube b cube upon a square plus b square is torque. So this is equivalent to gj theta dash. So the g, the rotational inertia for ellipse, is pi a cube b cube upon a square plus b square. Extremely important analogy. So moment you know eccentricity and semi-major axis, you know the g of the elliptical solid section. This is another important result that we looked at. Now having known this, the task for us is to find out the warping function, right? So let us look at the warping function now. To look at the warping function, we have to first find out stress, tau zx, right? Now everything is known here, the constant is known. So the constant, let us substitute back, right? So phi is nothing but g theta dash a square b square upon a square plus b square, x square upon a square plus y square upon b square minus 1, right? This is the constant, correct? If this is the function, then tau zx, which is going to be the differentiation del phi by del y, right, is going to be 2ty upon pi a b cube, right? Why is this suddenly the outcome? Simply because what we are saying is we have been substituting these numbers, correct? So what we said is that the stress function, which is going to give me introduction to this nomenclature of del x del y, is going to give me tau zx, which is just a differentiation of this phi, and then I used t by gj theta dash, right, to substitute. So what I have done is to substitute g theta dash, I have used t by g, right? This is what I have done, and this is going to give me 2ty, so 2y by b square. Let us look at this. You may be feeling confused, right? So del phi by del y is g theta dash. A square b square upon a square plus b square is fine. G theta is nothing but t upon j, because t is g j theta dash. So t upon j, what is j? Pi a cube b cube upon a square plus b square. So I have used this to my advantage to eliminate some of these problems. So t upon pi ab is what g theta dash is. This entire constant left with us. And then the only variation is 2y by b square. So this b square will come out and negative sign will prevail because it is a positive del phi by del y. So this is the outcome. Tau zy, which is minus del phi by del x, right? Minus del phi by del x will again be 2tx upon pi a cube b. Similar analogy. Now the only thing that will remain is this a square, so it will come here and sit with this. So these two are known. If these two stresses are known, del w by del x is going to be minus 2ty upon pi ab cube, right? Plus theta dash t upon gj, a square plus b square upon a cube b cube, so fine, right, into y. What I am doing is del w by del x plus del u by del y, del z is tau zx upon g. Are you extremely clear about this? I have used the strain relations to derive based on the displacement fields del w, the first principle. Now I am actually substituting the values. So del w by del y similarly would be 2tx upon pi a cube b g, so g is going to go also here, right, minus t by g pi a cube b cube x a square plus b square, because it was theta dash x and here it is theta dash y, plus and minus signs. So I know variation of w as a function of x and y. Del w by del x is function of y, is some function of y, and del w by del y is function of x. So w is f of x y plus constant, and if I differentiate this, f dash x y is equal to y. So now I am very clear where am I heading towards. So w has to be some alpha xy. See the mathematical induction. Del w by del x is fy, del w by del y is fx. So w has to be a form of this, so that f dash x eliminates this and makes only y outcome, right? Plus some constant, possibly, right? That's how it has to be. But w warping on the edges has to be 0. So see the induction, what I am doing. So I know at least qualitatively how w is going to look like, and that is most important achievement for me. So I can rub this now, right? So I have found out the stresses. So this is done. Inertia is found out completely. Prandtl function is completely found out. Stresses are found out. Now we are looking at warping, and then that completes our entire solution. If I integrate this, right, I have to take this out. So what we are saying is t by g pi a b cube will come out, a square plus b square upon b square, right? Y will also come out. So t y, so I am taking out everything, right? Let's circle, good practice, so that we know exactly what has come out. So only a square is left, right? B cube can come out very clearly, right? Minus 2. That is what I am left with. So this will become b square minus a square, because minus 2a square. Now this can come out. Now it is much easy form to handle, right? b square minus a square x plus some constant y. So w from this first equation will give me on integration this all constant which has come out into x plus f of y, some f1. Now we don't no longer need this equation. Here similarly, second equation will give me t x b square minus a square y upon g pi a cube b cube plus f2 of x. So that this equation holds true, same thing has come out, right? See, in both the cases everything is constant, alpha xy, see, very beautifully. Now if these two functions have to match, these two have to be 0, so there is no constant of integration, right? So w is nothing but t b square minus a square upon pi a cube b cube g xy. That's it. So that when x is equal to y equal to 0, w becomes 0. So warping function is also solved. Look at this b square minus a square. A is going to be always more than b. So w is going to be negative, which is also expected, the negative twist. So for ellipse, we have found out all the properties. The twist, right? Theta dash, which is nothing but t by g. So t by g, j is equal to theta dash has also given me what is the twist rate. Formally we can write this t upon pi a cube b cube g into a square plus b square is my theta dash. So I know twist, I know warping, I know these stresses, and I know the function. So ellipse as a cross section is the third problem that we have solved. Now after having this slightly heavy mathematical problems, let us look at few qualitative problems as well. A composite circular, this is GATE 2013 by the way. Composite circular shaft is composed of steel core surrounded by aluminium annulus. So it is this composite bar. So this is SS and this is aluminium. Okay, that is given. Perfectly bonded to each other. This is problem number 4. Right? They are perfectly bonded to each other and it is subject to pure torque. Then what would happen? And the options are only shear stress is continuous across steel aluminium surface. So stress, we know there is no longitudinal, there is no stress which is of this nature, right? So we are not worried. So I will not keep calling it shear stress, we know implicitly. Stress continuous across SS aluminium surface, aluminium transition. Second option is strain is continuous across. So moment, you see this problem, this is one rod, right? If this was only one bar, then there was no problem. It was independent, right? So we would have given this ideal zero warping solution of a solid rod. But now there are these composites. So we have to find what is this transition, and you will always encounter in aircraft the composites, right, which are made of something similar like this. So very, very practical problem. Third is both are continuous. Fourth, neither is continuous. Now, the shear stress depends on the property of the material, right? Tau as proportionality constant G. G of these two are different. So shear stress can never be constant, but they are glued or bonded together, which means the twist they are going to experience has to be same. Otherwise, if there is this one bar, so we can demonstrate it this way. If there is one bar inside which there is another bar, and these are not bonded but free to rotate with respect to each other, based on their material properties, they would have different twists, different theta dash. But if SS moves by this angle theta and aluminium by theta 2, you would see a slip. The slip is not allowed, which means depending on, this is like a thermal problem, depending on which tries to twist more, second will resist. So there is going to be opposite stresses formed. So stress can never be continuous. So these options are gone. This option or fourth is problem. But as we said, since it is bonded, none of them can have independent twist. And if the twist is the same, the theta dash, the warping is 0, because we have seen the displacement fields u and v will dictate that your gamma zx and gamma zy are identical in SS and aluminium. Because otherwise there would be a slippage and there would be a material coming out, which because of bonding is not allowed. So in bonded composites, stress cannot be continuous because of different material property, and in fact to hold them together, this glue is getting that additional stress. So glue is getting stressed, or the weld is getting stressed with that difference of shear stress between SS and aluminium. If SS has lower stress because of higher G property and aluminium has more, that delta is balanced by those bond that keeps them together. Another insight. Right? So this is the gate problem that we looked at. Then let's look at one more problem. Okay, this is an interesting problem. The stiffness cross-section of a long, slender, uniform structural member is idealized as shown in figure below. Okay. So this is another gate examination question. You have A, B, C, D. This is 500 mm. This is 200 mm. Okay. Now, these are the dimensions given. These each are 5 mm thick. So each web ABCD are 5 mm thick, and it is subject to a twisting moment of 10 kilonewton meter. Okay, so it is given. The magnitudes of shear flows in the web QAD, QDC, QCB, QBA are respectively, and answers given are 20, 20, 20, 20, 0, 0, 50, 50, 40, 40, 0, 0, all 50. Okay. So two options are symmetric and two are non-symmetric. And you should not start guessing the answers just because something comes and intuitively thinks in your mind. The cross-sectional areas are given now to be 3 centimeter squares. Okay. So the limbed areas at ABCD have cross-sections of 3 centimeter square. Okay. So these are all given. Now, twisting moment is already given. Wall thickness is very small, right? So what you should get from here very simply is that if you have to find out what is happening to this, you have to use this analogy. T is equal to 2AQ. The stress flow, we have seen the shear stress flow, right? So if you look at the area, qualitatively first of all, these options can be eliminated. Why? If shear flows are different, at the limbs there is going to be net movement, and this cannot sustain the bonds, which means the shear flow has to be uniform. It is a closed section, and for a thin section it is simply given as 2A into shear flow rate. What is area A? It is 50. So 500 mm is 0.5 meters. So 0.5 into 0.2, which is 0.1, right? Because 0.5 into 2 is 1. So this is 0.1. So 2A is 0.2. So Q is simply 10 upon 0.2, which is 50. So this is the correct answer. See, very, very important arguments that I first made to eliminate these two. The shear flow cannot have variation within these two. Why? Otherwise the effective total load would change, and then there would be a torque, But for a uniform torque for a closed section, which is a closed loop, cannot be non-zero. It has to counteract exactly this. So T is 2 into area of this into the shear flow rate. So that's why shear flow is uniform. And once I calculate, I eliminated option 1, which was 20, just from mathematics. Next question. Next question is actually from another gate point of view. A 3-stringer thin sheet beam with cross section like this is given. So it has this section, okay? This is 3 meters. So this dia is also 3 meters. Okay. Now T55 is given out to be 0.001. T11 is equal to T44, which is equal to 0.0015. So the thicknesses are also given. G is 20 GPa and tau allowed, the stress allowed, is 250 MPa. We have to find theta, the angle of twist. Okay? This is extremely important result, by the way. This is a cross section, the sectional view, right? Now rather than becoming actually an ellipse or a circle, it is this open-ended section with these thicknesses, right? So we have to find out the shear flows, what is happening, and based on shear flows we have to substitute these taus. So first we have to find the area. Since these are rectangular, right, because this is 3 and 3, it means this is 90 degree and these are 45 degrees equal. So the area of this cross section is half pi r square plus half into p square, which is this base, which is nothing but pi by 2. Radius is given, right, plus, I'm very sorry, my sincere apologies, this is not 45. The question actually corrects itself. So this is given as 2. So this is right angle but with different angles. So the radius is 1 plus half into BH, the base into height, right? So 2 into 3. So it is pi by 2 plus 3, which is 4.57 meter square, because this can be taken as 1.57. So 4.57 is the area, right? See how quickly I did this calculation. Now T upon 2A is going to be Q, which is T upon 9.141 Newton meter. If this is torque T, right, theta is nothing but Q upon 2AG integral of ds upon T, right? We have seen this shear flow. Now what will be this integral? This integral ds upon T, which I have to find out, is nothing but, area is known by the way, right? 9.141 into G is 20, which is GPa. Okay? So this is GPa, this is Q. ds upon T is going to be 2 pi upon 2 into T55. So thickness along this is 2 pi upon 2 into 0.001 plus along this is going to be 3, because S is nothing but this is 2 pi r. So 2 pi upon 2 into this, right, upon 3 into T11. T11 is nothing but 0.0015, right, plus 3.6, right, this is the diagonal, 4 plus 9 square root of 13, and this number is provided as approximately 3.6 upon 0.0015. This is integral of ds upon T. If I quickly look at this 2 is going to go out and this is becoming 1000 pi, right, because 0.001 is 1000 pi, 3140. this is going to be 0.015 into 30, so 0.15 into 300, 1.5 into 3000, 15 into 30,000, so this is 2000. See how quick mathematics I am doing. 36,000 upon 15, right? 2,400, right? So 7,540 is the value of this ds upon t. This is theta. Now, once we know this, we also know from this relation of theta, which is t upon 9.14a, the shear flow, right? That if I compare these two, shear flow is uniform across. So Q upon T11 is the stress which is allowed. Now you have to be very smart. Thickness which is actually maximum, right, is where tau is going to be here for a given shear flow. Here the shear stress is higher than the straight wall, correct? Which means I have to look at the least thick, because here, because thickness is higher and same shear flow is everywhere, the stress is going to be more than this. So tau 55 is more than tau 11 because it is this relation. So I have to use Q allowed as 250 MPa into the T11, which is 0.001. So 25 into 0.1, which is 2.5. So 0.25. Right? And this is further substituted as T, and so you would get theta as 9.1 T upon G. See how I solved it? I looked at allowed Q, which I substituted here, and then I looked at the twist. So I substituted it as 0.25 into 7,500 and I got the theta value. So the maximum theta value then can be based on the minimum, right? This is the fifth problem that we have solved. This gives us a reasonably good flavor of torsion and the torsional problems. And the outcome is, with this tutorial, we have closed the entire torsion section and how the problems are solved.